And we're going to start today with, our first speaker is going to be Shubadeep. And you know him from the department. He works with Chris Algar. I want to say he's been here for almost 4 years. Is that right?
3.5.
3.5, almost four. And he has a bachelor's and a master's of science in geological science from the Indian Institute of Science and Education and Research, IISER. That's if you want to say it in short form, from Kolkata, India. And go ahead, take it away, make it full screen.
Yeah, sure.
Renewable energy capacity.
Okay, can everybody see my screen? Can you see my screen, Dave?
Yeah, it looks great.
Yeah, sure. Thanks for the opportunity to give a talk for me. Hold on. Yeah. So today I'll be talking about importance of non-local benthic nitrate uptake in a semi-enclosed estuary. So if you see the title of my talk, it talks about nitrate. So it's a part of the nitrogen cycle. By the way, feel free to interrupt me if you have any question, because as Dave said, it's like pretty much informal. So that's it. So the motivation. So why we need to study nitrogen cycle? So you know that nitrogen cycle, nitrogen is one of the major building blocks for life. So nitrogen is, for biological or like environmental perspective, can be classified into two broad classes: biounavailable and bioavailable form. So the biounavailable, which is the nitrogen gas, which is the majority of our atmosphere, is not really useful for most of the organisms. Is the bioavailable form of nitrogen, which is mostly available for marine life, and it's also one of the major component in the rate field ratio. This bioavailable form of nitrogen is also a limiting nutrient in oceans, especially for the primary production, especially in the coastal area. So as with the climate change and increased human activities, this bioavailable form of nitrate or ammonia is increasingly it's increasing in proportion in the water bodies, which is, right now it's almost the anthropogenic input is almost as much as the natural input. And this increased load of anthropogenic, this fixed nitrogen causes eutrophication and harmful algal blooms and increased hypoxia and oxygen deficit zone in the oceans. So it's kind of, not really environmental friendly in most cases. So nitrogen cycle, that means we have a nitrogen fixation mechanism and a nitrogen removal mechanism. So we'll mostly be talking about nitrogen removal in this case, like focusing on. And the two terms that I'll be using mostly is benthic, that means sediment, and pelagic means water. So nitrogen cycle can be, seen in a very simple term as a nitrogen fixation, which is, nitrogen gas is being fixed by a certain group of organisms called diazotrophs in a bioavailable form, and then, incorporates into the organic matter, and then it gets recycled by ammonification and deNRA. These are the two. That means the bioavailable form stays in the system. So the nitrogen recycle can happen in anoxic system or in oxic system, and then comes the nitrogen removal part. That means bioavailable form to biounavailable form. That is the nitrogen gas, and this generally happens in the anoxic condition, like almost always happen in the anoxic condition. and also mostly in the benthic system, benthic, that means in the sediment, in the coastal regions where the sediment is anoxic in most part. The two pathways by which the nitrogen removal can happen is denitrification and ammonia. Now, let's see the study area where we did this study. So this is Bedford Basin, as you all know. That Bedford Basin is just beside Halifax. So this is a seasonally stratified estuary, which is very stable during the summer, and this deep water is pretty stable during the stratified period, which is the summer, and generally during the winter mixing, this system gets flushed by fresh water from the surface. So the proximity of BIO, which is Bedford Institute of Oceanography, they collect a long-term time series from different depths in the deepest part of the Bedford Basin. So you have a nice climatology. So so keeping, I mean, putting these things in perspective, you can see the deep water of Bedford Basin shows a nice seasonality throughout the year. You can see during the late winter or early spring, the water is pretty much oxygenated due to the winter mixing. That is, surface water is being mixed with the deep water, and then with the certification in the late in the year, the oxygen keeps dropping steadily. That means the deep water is kind of isolated from the top water, and you can see the oxygen drawdown. Also, you can see the ammonium climatology, that ammonia starts to build up. That is, after the spring bloom collapses, the ammonification happens, which releases the ammonia from the organic matter, and ammonia accumulates. And then after a few months, it starts to drop with accompanying by increase in nitrate. That means the nitrification takes over, and nitrification is converting the ammonia to nitrate. So in this, so this is a annual cycle. So it gives us an opportunity to look into the system at different parts and study different parts of the nitrogen cycle. So so here we'll be generally talking about the benthic system. So for that purpose, we go to the field a few times in the year, generally 4 times in different seasons. We collect sediment core sample using multi-core, and this is recovered core, and we bring it back to the lab. And in the lab, we generally do two kind of things, which is one is X-ray to benthic flux measurement, where we see the sediment water interface flux of oxygen and nutrient. We measure it, and we also measure the pore water chemistry of the core. Like, say, from different depth of the sediment, we take pore water and then analyze its nutrient to get a depth profile. We then use these data to constrain a full diagenetic sediment diagenetic model, which can be expressed essentially by these two equations. This is basically a reactive transport equation. So this sum R means this is all the coupled biogeochemical reactions, and these two are the transport term. So this term is the diffusive transport, and this is the advective transport. And these two denotes the two different phases of sediment. One is pore water, and this S means the solids. Okay, so the coupled reaction that I talked about. So this is all the reaction, most of the reaction that are included in the model essentially consist of oxic remineralization, nitrification, oxygenation of organic matter, and denitrification, and say in other forms of organic matter breakdown following the Gibbs-free energy yield, which is metal oxides and then sulfate oxidation, sulfate reduction, and so on. So yeah, so so In the title, I used a term called non-local benthic uptake. So traditionally, what we generally see as the the mode of transport is diffusion. However, there is another thing that can happen, which we call it non-local transport. Non-local transport means which is non-diffusive and is generally mediated by active biological processes, such as bioirrigation, like by some benthic macrofauna and all those kind of stuffs. Some other organisms can do it too, which is nitrate storing faculated bacteria or benthic denitrifying foraminifera. This kind of organisms, they can preferentially take bottom water for nitrate or some other nutrients, and can use it for their respiration. So DNRA and denitrification are two of the processes that can be mediated by non-local transport. So from the circumstantial evidences, we will be considering the benthic denitrifying foraminifera as one of our transport processes in the mechanism, in the modeling. So we parameterized our model with the constrain the model with the measurements that we did in the February 2019 field. So you can see the benthic flux. If you see the benthic flux of oxygen and nutrients, you will see that the nitrate is there is a high influx of nitrate into the sediment, um, which when we started to model, was pretty hard to get it without any non-local transported parameter reaction. When we consider the foraminiferal uptake of the nitrate, we could recreate the high influx of nitrate. So, and this is doing the denitrification according to the reaction. Uh, so when we calculated the percentage of denitrification carried out by bacteria and versus foraminifera, we found that more than 60% of the benthic denitrification is done by non-locally transported nitrate, the extra nitrate that is being uptaked by the system. Okay, just for a comparison, if we do not include that non-local transport, then could not get, we could not, predict the high nitrate influx that was observed on the field. So next, what we wanted to do is to get a prediction of the benthic flux throughout the year. So for that purpose, we used our model, which was parameterized as of February setting, and we applied that model, and we used that model and applied it transiently throughout the year. And the climatology of the bottom water that I showed early, in the beginning, was used as a boundary condition. So this is the model output that we get. So you see these points. So these are the points when we went to the field at different time points of the year, and you can see that. And this is for oxygen, and this is for the nutrients. So you can see that these are not exactly aligned, but they are close to each other. Like the modeled and the observed are close. We do not expect them to be exactly matched, because the conditions we are using is a long-term climatology as a boundary condition, but these measurements are of particular day or the particular time of the year or something like that, right? So they will be different, but we can expect to see the similar trend. So for these 3 points, time points, we can see kind of very close the prediction and the observation. However, at this point, we can see a large anomaly between observed and model fluxes. So what what could be the cause of it? So we are thinking that maybe this is caused by DNRA in the system. So till now we did not consider DNRA as one of the system reaction, because we generally parameterize our model with this observations, and for this observation we did not had to use DNRA as one of our processes. But for this one, it seems that we may need to DNRA as one of the biogeochemical reaction going on. So DNRA generally is mediated by Thioplica or Bagiotoa type of bacteria. So they are generally filamentous bacteria, and we did observe some of the filamentous stuff during our field in November. So next step would be considering this as a process and see if we can get it. So that would be the next step for me. So in a summary, we can see that this diagenetic modeling can be helpful in identifying unknown biogeochemical process in a system. So if you model it, if you can predict whatever you see, it's fine. And if there is a discrepancy between modeled and observed data, you can assume that some of the processes you are missing, and that's how you identify new processes. And this non-locally transported or biologically transported nitrate can either be removed from the system through denitrification or recycled by DNRA. And foraminiferal denitrification that we think we are identifying in this system can be a major sink for bioavailable nitrogen in the sediment. And also, if that it is true that DNRA is dominant here and foraminiferal denitrification is dominant here, that means there will be a competition between these two species for nitrate. Maybe the forams are motile, so they may have a competitive advantage down the line, but DNRA might have a short-term, competitive advantage, and then it is being, winning by the foraminiferas. So this competition can be, examined in this system. So yeah, so that's all. Thanks for listening. And if you have any questions,
Just imagine I'm clapping for everyone here. Okay. Maybe, yeah. If you want to raise your hand in the participants side window, if there's any questions, we have time for one question. I'll say. Scanning. No hands raised. Waving.
Celestine have a question.
Okay. Stormy has got a question.
Celestine, yeah. Okay.
Go ahead, Stormy.
Maybe the microphone is muted.
No, Stormy. Oh, couldn't find the wave button. That was the question was actually not a question, but it was applause. Okay, well, I don't see any other questions, so we're going to move on to the next speaker. And wait, Jinyu's got a question. Go for it.
I raised the hand.
Yeah.
Okay,
good.
so very good talk. And just a question. So you have a model. So
Yes.
and reasonably okay for like winter, summer, but doing poorly in the fall, right? So I just wonder how good is the boundary condition? Basically the boundary condition at the top boundary condition, right? So the water, near bottom water, kind of nutrient option, etc. How does that play the role for the model performance or deficiency?
Yeah, so yeah, that's true. I mean, so if you see the boundary condition that I used here is a long-term climatology. So what might happen that the nitrate uptake may be directly proportional to the available nitrate concentration in the bottom water, right? So if there is a high bottom water nitrate, then the uptake would be much more than if it is low. If it is directly directly correlated. So that might definitely have an effect. So so it's essentially using the nitrate, right? So nitrate, if you have low nitrate, that means the nitrification would also be pretty much low. So that's how it will be, contributing towards different fluxes. Also for oxygen, similarly, if you have low oxygen, then the oxygen related, the remuneration or nitrification on all those kind of steps would be much lower, whereas in the high oxygen condition. So that's how they would be different, and that's how the boundary conditions would differ what we see in the processes with changing condition. Yeah.
Thanks.